Hello there, and welcome to the Sleep Journal. Tonight, we are exploring something almost too small to imagine. Cosmic dust, tiny grains, drifting quietly through the space between the stars. Some are smaller than a speck of smoke. Others are barely visible, even under a microscope. It sounds like nothing at all, but this dust built everything you know. Every star, every planet, every mountain, ocean, and living thing. All of it began as scattered grains of dust, drifting patiently through the dark. Tonight, we follow that dust on its long journey. From the death of ancient stars to the birth of new worlds, from the faint glow above your horizon before sunrise to grains older than our own sun, found inside meteorites on Earth. This is not a fast story. It moves slowly, the way dust itself moves. Patient, unhurried, taking exactly as long as it needs. Before we begin, if evenings like this help you drift off, feel free to like, subscribe, or leave a gentle comment below. It helps other tired minds find their way here. But for now, there is nothing you need to do. Let your jaw unclench. Let your shoulders drop. Let your breathing slow down completely. Imagine tiny specks of light drifting gently through darkness. No rush. No noise. Just quiet, endless drifting. Let us begin. Astronomers estimate our galaxy holds an almost unimaginable amount of this material. Spread across a disk 100,000 light-years wide, in most places, it is impossibly thin. A single grain, floating within a space the size of a small room. And yet, thin as it is, this dust has shaped nearly everything we see in the night sky. It blocks starlight in some places. It scatters it gently in others. Slowly, over unimaginable stretches of time, it gathers together and becomes something entirely new. A star, a planet, a quiet, spinning world, somewhere in the dark. Tonight, we let that same patience settle into our own bodies. There is no need to rush toward sleep, only a slow, gentle drift, exactly like the dust we are about to explore together. Consider, for a moment, how strange this actually is. When most people picture the vastness of space, they picture emptiness, black, silent, and mostly featureless, except for the occasional bright point of a star. And in many ways, that picture is correct. Space genuinely is close to empty, far emptier than the finest vacuum any laboratory on Earth could ever produce. But close to empty is not the same as completely empty. Scattered through that vastness, in concentrations so low they barely register, are these countless tiny grains, left behind by generation after generation of stars, drifting patiently, waiting their turn to become something else. Tonight, instead of thinking about the stars themselves, the bright, dramatic endpoints of stellar life, we are going to spend our time with something quieter. The dust in between, the raw material. The part of the story that rarely gets told, because it does not shine and does not explode. It simply drifts, slowly, for as long as it needs to, until its moment finally comes. There is something worth noticing in how little attention this material usually receives. We celebrate stars. We name constellations after heroes and animals. But the dust between them, patient and unremarkable, rarely earns a mention at all, and yet, without it, none of those stars would exist in the first place. Tonight, we give this quiet, overlooked material the attention it deserves. Slowly, gently, exactly the way it deserves to be considered. To put this scale into perspective, our own solar system contains only 8 planets, circling a single star. But if you added up every star in the entire Milky Way, along with every planet orbiting them, that number would still be smaller than the total mass of dust scattered quietly between them. It is a strange reversal of how we usually picture the universe. We tend to think of space as something organized around bright points of light, stars, like small islands, scattered across a dark, empty sea. But most of the material in a galaxy is not bright at all. It is dim, cold, and patient, waiting quietly in the spaces between those islands. Tonight, that dim, patient material is exactly where we are heading. Every culture throughout human history has looked up and wondered about the dark spaces between the stars. Some imagined rivers of milk stretching across the sky. Others imagined pathways for spirits, or roads connecting the living to the dead. None of them knew, of course, about the true nature of that faint, glowing haze. But they were right to notice it, and right to wonder. Tonight, we simply add the missing piece to that ancient wondering, filling in gently what earlier generations could only imagine. To understand cosmic dust, we start with something surprising. Nearly all of it once lived inside a star. Every heavy element in the universe, carbon, oxygen, iron, silicon, was forged deep within a star's core, built slowly, through nuclear fusion, over millions or billions of years. But stars do not keep these elements forever. When a star reaches the end of its life, it releases much of that material back into space. For a star like our Sun, this happens gently. In its final years, it swells into a red giant, slowly shedding its outer layers into the surrounding darkness. For much larger stars, the ending is far more dramatic. They explode as supernovae, blasting their contents outward in an instant, scattering newly formed elements across enormous distances of space. In both cases, something remarkable happens as the gas expands and cools. Atoms of carbon, oxygen, and silicon begin finding each other. They bond together, forming tiny solid grains, one atom at a time. This is the birth of cosmic dust. It condenses directly from the outflow of a dying star. In much the same way steam turns into droplets of water as it cools, astronomers have watched this happen in real time. Using telescopes trained on stars nearing the end of their lives, they have seen dust forming in the outer layers of aging stars, and in the debris left behind by recent explosions. One famous example came from a supernova observed in a nearby galaxy. Years after the explosion, astronomers found enormous amounts of freshly formed dust, far more than anyone originally expected. Multiply this by billions of stars that have lived and died throughout our galaxy's history, and you begin to understand where all this dust actually comes from. It is, quite literally, the ash of dead stars, drifting slowly through the darkness, patiently waiting for its next transformation to begin. The rate at which this happens varies enormously depending on the type of star involved. A star similar in mass to our own Sun spends roughly 10 billion years quietly fusing hydrogen into helium, before finally swelling into a red giant and shedding its outer layers gently over thousands of years. A much more massive star, 10 or 20 times heavier than the Sun, burns through its fuel far more quickly, sometimes in only a few million years, before ending its life in a single, catastrophic explosion. These massive, short-lived stars are disproportionately important dust producers, because supernovae are capable of forging and scattering vastly larger quantities of heavy elements in a single event than a smaller, gentler star could ever produce across its entire lifetime. Astronomers studying supernova remnants have found dust particles of many different sizes, ranging from grains far smaller than anything visible under an ordinary microscope, to somewhat larger clumps, though nearly all of it remains, by everyday standards, extraordinarily fine. Once released, this dust does not remain near its parent star for very long, at least not on cosmic timescales. Stellar winds, radiation pressure, and the slow rotation of the galaxy itself all work together, dispersing this material outward, mixing it gradually with the broader darkness of interstellar space, until, over the course of many millions of years, it becomes almost impossible to trace any single grain back to the exact star that once produced it. One particularly striking example came from a supernova studied closely by astronomers, observed in a nearby galaxy known as the Large Magellanic Cloud. Years after the initial explosion, researchers detected large quantities of newly formed dust within the expanding remnant, far more than anyone had originally expected to find there. This single discovery confirms something important. A single supernova can seed the surrounding space with an enormous amount of raw material, almost instantly, on a cosmic timescale. Compared to the slow, gentle shedding of a smaller, dying star, astronomers continue monitoring this same supernova remnant even today, watching as the dust within it slowly cools and spreads further into the surrounding space. Each new observation adds another small piece to our understanding of exactly how quickly and how much dust can form in the aftermath of such a violent event. It remains one of the clearest, most direct examples we have of dust formation happening in real time, rather than something inferred only through distant, indirect evidence. This kind of direct confirmation matters enormously to scientists, since so much of astronomy relies on careful inference rather than direct observation. Having even one clear, confirmed example strengthens confidence in every other case where direct observation remains impossible. Once scattered into space, dust does not simply sit still forever. Over millions of years, gravity slowly pulls it together with surrounding gas, forming vast, cold clouds that astronomers call molecular clouds. These clouds can stretch for hundreds of light years across, containing enough material to eventually form hundreds of thousands of stars. Within these clouds, dust plays a role far more important than its size suggests. Each tiny grain acts almost like a meeting place, a surface where atoms and molecules can land and slowly react with one another, forming more complex compounds than could ever form freely floating in open space. Many of these grains become coated in thin layers of ice, frozen water, carbon monoxide, and other simple compounds. Built up slowly, over thousands of years, in the extreme cold of deep space, dust also plays a second important role here. It blocks light almost completely. A dense molecular cloud, thick with dust, can appear as a dark patch, set against the brighter, glowing backdrop of the galaxy beyond it. This is why some of the most famous features of the night sky are not empty voids at all. They are simply regions thick with dust, quietly hiding whatever lies behind them. Deep within one of these dark clouds, gravity eventually begins to win. A dense clump of material starts collapsing in on itself, drawing in more gas and dust as it continues shrinking. Eventually, if enough material gathers, the center becomes hot enough to ignite. A new star is born, deep inside that same quiet, dusty cloud. Molecular clouds themselves are surprisingly cold places, often only a few degrees above absolute zero, the coldest temperature theoretically possible. At those temperatures, chemistry behaves very differently than it does here on Earth. Reactions that would happen instantly at room temperature can take thousands of years inside a molecular cloud, simply because atoms and molecules are moving so slowly and colliding so rarely in such thin, cold surroundings. This is precisely why the surface of a dust grain becomes so important. It gives wandering atoms a place to land and enough time sitting still for a reaction to finally occur. A reaction that might otherwise never happen at all in the open cold of space. Over the past several decades, radio telescopes have identified an astonishing range of compounds drifting through these clouds. Simple molecules like water and carbon monoxide, but also far more complex organic compounds, some of them remarkably similar to molecules found in the chemistry of living things here on Earth. This has led some scientists to wonder whether the earliest chemical building blocks of life itself might have first assembled not on a young planet at all, but earlier still, quietly, patiently, on the cold surface of an ordinary grain of interstellar dust, long before any planet ever existed to receive it. It is a strange and quiet thought to sit with, that the earliest steps toward chemistry, and perhaps eventually life, may have happened not on any world at all, but simply on the surface of drifting dust. Deep space itself may have quietly hosted the earliest steps toward biology, long before Earth, or any planet at all, ever came into being. This idea remains speculative, of course, but it reshapes how scientists think about the raw ingredients of life, not something that appeared suddenly on a young planet, perhaps something slowly assembled, patiently, on the cold surface of ordinary dust, long before there was ever anywhere for it to land. Some researchers studying meteorites have even found trace amounts of amino acids, the basic building blocks of proteins, locked away inside ancient, undisturbed rock, suggesting that at least some of this chemistry may have formed long before Earth existed, drifting patiently through space, eventually arriving here as part of the same slow, ongoing process that builds stars, planets, and everything else. Around this newly formed star, a thin disk of leftover material continues to swirl. Astronomers call this a protoplanetary disk. Within it, the same dust that once floated freely begins an entirely new journey. One that will eventually lead to full planets, moons, and comets. This process begins with grains barely larger than particles of smoke, drifting slowly within the spinning disk around a young star. Through gentle collisions, these tiny grains begin sticking together, held loosely by weak static forces, similar to dust clinging to a balloon. Slowly, these fragile clumps grow larger, from grains to pebbles to small, rocky chunks. This early stage remains one of the more mysterious steps in planet formation. At a certain size, objects should, in theory, bounce apart rather than merge. And yet, across countless young solar systems, this barrier is somehow overcome. Once objects reach roughly a kilometer across, gravity itself takes charge. These larger bodies begin pulling each other together through their own attraction, growing steadily larger through repeated collisions. Over millions of years, every rocky planet in our solar system formed exactly this way, built slowly from the same dust that once drifted freely through space. Even gas giants like Jupiter and Saturn owe their existence to dust. Their solid cores likely formed first, through this same slow accumulation process. Only later did their gravity pull in the vast clouds of gas we see today. Comets preserve an even earlier stage of this story, loose collections of dust and ice, largely unchanged since the earliest days of our solar system. It is worth pausing on just how long this entire process takes, from beginning to end. From the moment a molecular cloud first begins to collapse, to the moment a fully formed planetary system settles into a stable configuration, several million years typically pass, an almost unimaginable stretch of time by human standards, and yet remarkably brief when measured against the roughly 10 billion year lifespan of a star like our Sun. Astronomers have been fortunate enough to observe many young solar systems at different stages of this process, scattered throughout nearby star-forming regions, giving them something like a series of snapshots, each one capturing a slightly later moment in what is essentially the same long, patient story. Some young systems still show enormous, thick disks of gas and dust, largely unchanged, surrounding stars only a few 100,000 years old. Others show disks with clear, empty gaps carved into them, likely marking the locations where planets have already begun to form, sweeping their orbital paths clear of remaining debris. Still others, somewhat older, show disks that have thinned dramatically, most of their original material already gathered into planets, leaving behind only a faint, sparse remnant, similar to the thin disk of dust that still lingers, even today, within our own solar system. Some young systems, observed by powerful modern telescopes, show something even more dramatic: faint gaps and rings, carved directly into the disk by planets still in the process of forming. Astronomers can sometimes estimate the mass and location of an unseen planet simply by studying the shape of these gaps, much the way a footprint reveals something about the foot that made it, without ever seeing the foot directly. Some of the clearest images of these forming systems have come from powerful new telescopes, capable of resolving details once thought impossible to observe from Earth. Each new image reveals a slightly different stage of this same long, patient story. Rings, gaps, spirals, and faint clumps, each one a quiet clue about a planet still gathering itself together from the dust surrounding it. Every single planet we know of, including the one you are resting on right now, went through this exact same slow process. Grains sticking to grains, pebbles sticking to pebbles, patiently, over millions of years, until a full, rounded world finally emerged from what began as nothing more than scattered specks of dust. Cosmic dust is not one single, uniform substance. It comes in several distinct varieties, each with its own particular origin. The most common type is silicate dust, made mostly of silicon and oxygen, forming mineral structures similar to ordinary sand or rock. This type tends to form around cooler, oxygen-rich stars nearing the end of their lives. A second major type is carbon dust, sometimes compared loosely to soot, forming around carbon-rich stars, where carbon atoms bond into complex structures. Some of these grains contain structures remarkably similar to graphite, or complex ring-shaped molecules that some scientists believe may relate to early chemistry for life. A third category is icy dust, grains with a solid core, later coated in frozen water and other simple compounds. These icy grains become especially important far from a young star's warmth, serving as building blocks for icy moons, comets, and distant frozen worlds. Interestingly, the type of dust found in a region often reveals its history. A patch rich in silicate dust may point to a nearby, aging, oxygen-rich star. A patch rich in complex carbon compounds may point to a very different kind of stellar death. By studying the faint light absorbed and released by these different dust types, astronomers can trace individual grains back toward the stars that likely produced them, sometimes billions of years in the past. It is a remarkable thought. A single grain, drifting quietly through darkness, might carry a tiny, preserved record of a star that died long before our sun ever existed. The physical size of these grains also varies considerably, though nearly all of them remain far smaller than anything visible to the naked eye. Many interstellar dust grains measure somewhere between a few hundredths and a few tenths of a micron across, smaller than the wavelength of visible light itself, which is part of why they interact with light in such particular ways, scattering blue light more efficiently than red, and absorbing certain wavelengths almost completely, depending on their composition and shape. Some grains are roughly spherical. Others, particularly certain carbon-based structures, form elaborate, layered shapes, sometimes compared to tiny, imperfect onions, with alternating layers built up slowly over long periods of exposure to different chemical environments. As the grain drifted through varying regions of space, scientists studying these structures under powerful electron microscopes, using tiny samples recovered from meteorites, have found grains with astonishingly intricate internal structures, layer upon layer, each one recording a different chapter of that particular grain's long, slow journey through the galaxy, sometimes stretching back well over 4.5 billion years, patiently preserved, waiting quietly to finally be studied. Astronomers sometimes describe dust grains as tiny time capsules, each one carrying a fragment of history within its layered structure. Reading that history requires extremely delicate laboratory work, since a single grain may be smaller than a speck of pollen. Researchers use powerful instruments capable of measuring the exact ratio of different chemical elements within a single microscopic grain. From that ratio alone, they can often determine which type of star likely produced it, and roughly how long ago that star lived and died. It is patient, exacting work, requiring instruments sensitive enough to measure differences invisible to almost any other kind of scientific analysis. You are lying very still now. The day has grown distant. Your breathing has found its own pace. Slow, easy, unhurried. Imagine drifting gently through a vast, quiet cloud of dust, somewhere between the stars. There is no sound here, only a faint, soft glow, distant starlight, scattered gently by countless tiny grains, filling the darkness around you with a dim, silvery haze, like moonlight, filtered softly through a light morning fog. The dust here is impossibly thin, spread across trillions of miles, and yet it still catches the light just enough to soften the darkness. Just enough to make the emptiness feel less empty. Imagine floating slowly through that hazy light, weightless, unhurried, with nowhere you need to be. Each tiny grain around you has traveled here across an unimaginable distance, carried by the wind of some ancient, long-vanished star, drifting patiently for millions of years, with no destination in mind, simply following the slow, quiet pull of gravity wherever it happens to lead. There is something deeply calming in that patience. This dust is not in a hurry. It does not worry about where it is going or when it will arrive. It simply exists, drifting, content to let time do its slow work. Let your body borrow a little of that patience now. Let your shoulders soften and sink deeper into the bed beneath you. Let your hands rest, heavy and still, exactly where they are. There is nothing you need to do right now, and nowhere you need to be. Just this soft, silvery haze and your own slow breathing, blending gently together. Notice how little this quiet cloud around you seems to want. It is not reaching for anything. It is not striving towards some distant goal or measuring its progress against any deadline. It simply continues existing, exactly as it is, at exactly the pace that feels natural to it. And that alone seems to be enough. There is no part of this vast, drifting cloud that is anxious about tomorrow, or replaying yesterday, or wondering whether it is doing things correctly. It simply is, patiently, quietly, without effort. Let that same quality settle into your own body now, layer by layer. Let your forehead soften. Let your jaw loosen just a little further. Let your chest rise and fall without you needing to guide it at all. The way this dust drifts without needing to guide itself either. Somewhere in this same vast cloud, other travelers exist too, closer together in places, forming faint, ghostly wisps and threads, then thinning out again into near total emptiness. And yet the entire cloud somehow holds together, loosely, gently, connected by nothing more than the soft pull of gravity, working patiently across unimaginable distances and unimaginable time. Somewhere far ahead of you, deep within this same drifting cloud, a small, dense knot of dust and gas is slowly beginning to collapse. The first quiet stirrings of a star that will not be born for hundreds of thousands of years yet. There is no rush here, no deadline, only the slow, patient unfolding of something vast, taking exactly as long as it needs to take. And you, resting here tonight, are allowed exactly that same patience, exactly that same permission to simply drift, softly, towards sleep, taking exactly as long as you need. Let the last of today's thoughts drift away now, gently, the way a grain of dust drifts away from the star that once held it. Not forced, not rushed, simply released, softly, into the quiet dark surrounding you. There is nothing left to hold on to tightly tonight, only this soft, patient drifting, carrying you gently toward rest. Not all cosmic dust lies far away, among distant stars. Some of it drifts quietly through our own solar system, scattered along the same orbital plane where Earth and the other planets travel. This nearby dust comes from comets, shedding material as they pass close to the sun, and from countless small collisions between asteroids far out in space. Over billions of years, this debris has spread into a broad, thin disk, extending outward from near the sun, past the orbit of Mars. Under the right conditions, this dust becomes visible to the naked eye, in a phenomenon known as zodiacal light, on a clear, dark night, away from city lights, just after sunset or before sunrise. A faint, glowing cone of light can sometimes appear, rising gently from the horizon, along the same path the sun travels. This soft glow is sunlight, scattered off countless tiny grains of interplanetary dust, each one no larger than a fine grain of sand. Ancient civilizations noticed this glow long before understanding its true cause. Some cultures described it as a false dawn, appearing before the true sunrise. Persian astronomers gave it a name meaning roughly, the light before the light. This dust does not stay in place forever. It is constantly replenished by comets and collisions, and constantly lost, slowly spiraling inward toward the sun over thousands of years. Pulled gently by the pressure of sunlight itself, yet somehow, this reservoir remains remarkably stable, century after century, because new debris arrives just as steadily as old debris disappears. The zodiacal light is not the only visible trace of this nearby dust. Under exceptionally dark skies, far from artificial light, careful observers have occasionally reported an even fainter glow, appearing directly opposite the sun's position in the sky, known as the Gegenschein, a subtle brightening caused by sunlight, reflecting almost directly backward off dust particles, positioned precisely behind Earth in its orbit. This effect is so faint that it remains genuinely difficult to observe, even under ideal conditions. Many experienced amateur astronomers report never having seen it clearly in an entire lifetime of observing. Together, the zodiacal light and the Gegenschein form a faint, complete ring of scattered sunlight, tracing the entire plane of our solar system's dust disk across the sky. Largely invisible in ordinary conditions, but quietly present night after night, a soft reminder that even the space immediately surrounding our own planet is not truly empty, gently filled with the slow, ancient debris of comets and asteroids that have been contributing to this thin, glowing disk for billions of years. Some early astronomers mistook this glow for something else entirely, a distant, unexplained light near the horizon, appearing only under very specific conditions. It took careful, patient observation across many decades to properly separate this phenomenon from other, similar-looking effects, such as distant city lights or unusual atmospheric glows. Today, skilled amateur astronomers still travel to remote, dark locations, specifically hoping to witness this same gentle glow, a small, quiet reward for anyone patient enough to wait for exactly the right conditions. There is something fitting about that patience, given everything this glow represents. Billions of years of slow, steady accumulation, visible for just a few brief minutes, to anyone willing to step outside and look, and simply wait quietly for it to appear. Studying dust scattered across such vast distances is a genuine challenge for scientists. In most cases, they cannot simply travel out and collect a sample directly. Instead, astronomers rely mainly on infrared light to study dust from afar. Dust grains absorb visible starlight, warm slightly, and then release that energy as infrared radiation. By carefully analyzing this faint glow, scientists learn a great deal. Temperature, size, composition, sometimes even the rough age of the material itself. But in a few remarkable cases, scientists have gone even further, actually reaching out and physically collecting samples from space. One extraordinary mission, named Stardust, launched in the late 1990s. Its goal was simple, yet ambitious: fly close to a comet and capture tiny particles streaming off its surface. It used a strange, nearly weightless material called aerogel, sometimes nicknamed frozen smoke, capable of gently slowing fast-moving particles without destroying them completely. In the mid-2000s, this spacecraft returned a small capsule back to Earth, containing thousands of microscopic grains of cometary dust, material that had remained largely unchanged since the earliest days of our solar system. Scientists continue studying these tiny grains even now, searching for clues about the earliest chemistry of everything around us, locked away, undisturbed, inside particles that had drifted quietly through space for over 4 billion years, until a spacecraft finally reached out, gently, and gathered them home. The Stardust mission was not the only effort of its kind. A separate spacecraft named Hayabusa, launched by the Japanese Space Agency, successfully returned tiny samples directly from the surface of an asteroid, followed later by an even more ambitious successor mission that brought back larger samples from a different asteroid roughly a decade after that. NASA's own OSIRIS-REx mission carried out a similar feat, briefly touching down on an asteroid named Bennu, and successfully returning a substantial sample of surface material back to Earth. Each of these missions represents an extraordinary amount of patience and precision. Spacecraft traveling for years across millions of miles of empty space, executing maneuvers with pinpoint accuracy, all in order to gather what often amounts to only a few grams of material, tiny particles of dust and rock that nonetheless carry within them an enormous amount of scientific value, preserved records of conditions from the earliest days of our solar system, untouched by the geological processes that have long since reshaped the surface of Earth itself. It is worth appreciating how much careful planning goes into a mission like this. Years of design, years of travel, all leading up to a single, brief encounter with a small, fast-moving comet. Any small miscalculation could have meant returning with nothing at all. And yet, through patient, careful engineering, the mission succeeded, gathering material that would otherwise have remained forever out of reach. Scientists studying the returned aerogel had to develop entirely new techniques just to locate the microscopic particles trapped inside it. Volunteers around the world helped scan thousands of images, searching patiently for the telltale tracks left by each tiny grain as it slowed to a stop. This kind of collaborative, painstaking search eventually located thousands of individual particles, each one carefully extracted, cataloged, and studied, contributing another small piece to our understanding of comets and the early solar system. It stands as one of the finest examples of patient, collaborative science, ordinary volunteers and professional researchers working together toward a shared, unhurried goal. Deep within some of the darkest, densest clouds of dust, remarkable structures quietly take shape. Astronomers call them Bok globules, named after the astronomer who first studied them. These small, dark clouds are relatively compact by cosmic standards, often just a light year or two across. But they are extraordinarily dense, appearing as stark, inky silhouettes against brighter backgrounds. For decades, scientists could only guess what was happening deep inside them. Ordinary light simply could not penetrate their thick, shrouded interior. It was only with infrared and radio astronomy that researchers finally peered inside, confirming that many of these globules are indeed slowly collapsing under their own gravity. The earliest, quietest stages of a brand new star being formed. This collapse is an extraordinarily slow, patient process. A typical Bok globule may take hundreds of thousands of years to fully collapse. Throughout nearly this entire process, the forming star remains completely hidden, wrapped inside a thick cocoon of the very same dust feeding its growth. Only in the final stages does it begin to disperse the surrounding cloud, gradually emerging from its dusty shell, visible at last in ordinary light. Some of the most striking images ever captured show this exact process in progress. Dark, dusty pillars silhouetted against the glowing backdrop of a busy star-forming region, with faint points of infrared light revealing young stars, still hidden, quietly gathering mass. Bok globules rarely form in perfect isolation. More often, they are found clustered together within larger star-forming regions, sometimes dozens of them scattered across a single glowing nebula, each one representing a separate individual pocket of collapse, occurring at a slightly different pace and a slightly different stage. Some globules within the same cluster may already contain young stars nearing the end of their formation, while their neighbors, only a short distance away, remain almost entirely quiet, still tens of thousands of years from beginning any noticeable collapse at all. This staggered, uneven timing means that a single star-forming region can remain active for millions of years at a stretch, one globule finishing its transformation just as another, nearby, is only beginning its own long, slow journey toward eventually becoming a star. Astronomers have also found that the mass of a Bok globule tends to determine, fairly reliably, what kind of star it will eventually produce. Smaller, lighter globules typically collapse into stars similar in size to our own sun, or smaller still, larger, heavier globules are capable of producing far more massive, brighter stars, the kind that burn through their fuel quickly and end their lives only a few million years later, in a dramatic explosion, scattering fresh dust back into the surrounding cloud. ready to begin the entire slow process over again. Some of the most famous images ever captured by powerful telescopes show entire clusters of these globules, side by side, each one at a slightly different stage of its own long, quiet transformation, a patient nursery, scattered across many light years, quietly producing new stars, one at a time, for as long as the surrounding cloud has material left to give. Some of these star-forming regions remain active for tens of millions of years, continuously producing new stars long after the first generation has already begun shining. Eventually, the surrounding dust and gas becomes depleted, and the process slows, then stops entirely. What remains is a scattered cluster of young stars, drifting slowly apart from one another over many more millions of years, until the family that once formed together in the same quiet cloud is no longer recognizable as a single group at all. Our own sun likely formed this same way, once part of a larger cluster of siblings, born from the same collapsing cloud of gas and dust. Over billions of years, that cluster has scattered so completely across the galaxy that none of the sun's original stellar siblings can be identified with any real confidence today. They drift somewhere out there, indistinguishable now from any other ordinary star, quietly living out their own separate lives, unaware they were ever part of the same family at all. Cosmic dust is not confined only to the depths of interstellar space. A surprising amount of it reaches all the way down to Earth, falling gently through our atmosphere, quietly, every single day. Scientists estimate somewhere between 5 and 10,000 tons of space dust reach Earth's surface each year, spread so thinly across the entire planet that it goes almost entirely unnoticed. Most of this material comes from comets and asteroids, tiny fragments shed as they pass through the inner solar system. As these microscopic particles enter our atmosphere, most are far too small to burn dramatically. Unlike the streaking light of a shooting star, they slow gently in the upper atmosphere, drifting slowly downward over a period of weeks, or even months, eventually settling quietly onto the surface, indistinguishable from ordinary earthly dust. Scientists search for these particles in very specific places: the pristine ice of Antarctica, the deep, undisturbed sediment on the ocean floor, places where ordinary dust accumulates slowly enough that even a tiny trace of space dust can be identified. Under a microscope, many of these particles reveal telltale signs of their true origin: tiny, glassy, partially melted spheres formed briefly during their passage through the atmosphere. In a very real, physical sense, a small amount of space dust settles quietly around you nearly every day, drifting silently through the air, mixing invisibly with the ordinary dust of Earth. A quiet, continuous reminder that even here, at home, we remain connected to the wider universe. This gentle rain of dust is far from a modern discovery, though understanding its true origin took scientists a surprisingly long time. For centuries, occasional reports of unusual dust deposits were recorded without any clear scientific explanation. It was not until the 20th century, with the development of sensitive analytical chemistry and electron microscopy, that scientists could conclusively distinguish extraterrestrial dust from ordinary terrestrial particles, based on subtle differences in mineral composition and isotopic ratios rarely found together in rocks that formed here on Earth. Researchers studying deep ice cores, drilled from Antarctica, have even been able to track subtle variations in the rate of dust infall over thousands of years, occasionally correlating brief spikes in extraterrestrial material with specific known events, such as the breakup of a particular comet, or an unusually close pass of a known asteroid stream, offering a kind of slow, patient historical record, written not in ink, but in the quiet accumulation of ancient dust, layer by layer, year after year, largely unnoticed by anyone walking above it. The deep ocean floor offers a similarly patient archive. In certain slow accumulating regions of the seabed, sediment builds up so gradually, sometimes only a few millimeters every 1,000 years, that even tiny rare particles of extraterrestrial dust can remain identifiable within distinct sediment layers for millions of years after they first settled there. Researchers extracting long cylindrical cores of this ancient seafloor mud have, in a handful of remarkable cases, identified distinct bands enriched with extraterrestrial material, thought to correspond to specific ancient events, a nearby supernova explosion tens of millions of years ago, whose expanding debris eventually rained down gently onto Earth, leaving behind a faint, patient signature, buried quietly within the ocean floor, waiting patiently for millions of years, until scientists finally drilled down far enough to notice it. This kind of research requires extraordinary patience and precision, drilling through undisturbed ocean sediment without disturbing the delicate layering that makes the entire record meaningful in the first place. Researchers often spend years analyzing a single core sample, carefully cataloging each thin layer before drawing any conclusions at all. It is slow, careful work, matching the same patient timescale as the very dust it is designed to study. Some grains of cosmic dust are especially remarkable, older than the sun itself. Scientists call these prosolar grains, tiny particles that formed around other, ancient stars, long before our own solar system began to take shape. Somehow, they survived, largely unchanged, through the entire violent process of our solar system's formation. Finding them is extraordinarily difficult. Most of the material that built the sun and planets was thoroughly melted and mixed together. Only a very small fraction of the original dust avoided that fate entirely, becoming trapped instead within primitive meteorites, essentially frozen in time. Scientists identify these grains by carefully examining the ratios of different isotopes within them. Material formed within our own solar system tends to share a fairly consistent chemical signature. Prosolar grains, by contrast, often show dramatically different ratios. Chemical fingerprints that simply do not match anything formed here at all. Some of these grains are made of silicon carbide, others of pure carbon, in the form of microscopic diamonds or graphite. By studying their precise composition, scientists can often identify the type of star that likely produced each grain. Sometimes a dying red giant, sometimes a violent supernova explosion. Some of these grains have been dated as billions of years older than our solar system itself, meaning a small meteorite sitting quietly in a laboratory drawer contains fragments of stars that lived and died long before our sun was ever born. Holding such a meteorite, you would be holding, quite literally, a small piece of a star that no longer exists. The particular meteorite, where many of the most well-studied prosolar grains were discovered, fell to Earth in Australia. In the late 1960s, scientists quickly recognized it as an especially primitive type of meteorite, one that had experienced remarkably little heating or chemical alteration since the very earliest days of the solar system, making it an ideal place to search for material that might have survived from an even earlier era still. Over the decades since its discovery, researchers have returned to samples of this meteorite again and again, using increasingly sophisticated laboratory techniques, extracting and identifying thousands of individual prosolar grains, some measuring only a few thousandths of a millimeter across. Each one a tiny, durable survivor from the winds of some ancient, long-vanished star, could contain within it material old enough to predate the very sun that lit that afternoon sky. Every time researchers return to this same meteorite, new laboratory techniques reveal grains that earlier instruments were simply too coarse to detect. It is a strange kind of ongoing discovery, returning again and again to the exact same small rock, and finding something new each time, a reminder that patience and improving tools can reveal secrets hiding in plain sight for decades. Museums around the world now display small fragments of meteorites like this one, often behind unassuming glass cases, easy to walk past without a second glance. Yet within those quiet, unremarkable rocks rests material older than our entire solar system, a patient, silent testament to stars that burned out long before the sun ever gathered itself together from the same ancient cloud of dust. Somewhere in a quiet museum drawer or a research laboratory, these small fragments continue resting, exactly as they have for decades since their discovery, waiting, patiently, for the next curious scientist to examine them a little more closely and find something new, hidden quietly within their ancient, layered structure. On the grandest scale, cosmic dust helps shape the appearance of entire galaxies. Looking at photographs of spiral galaxies, similar in shape to our own Milky Way, one striking feature stands out: the elegant, sweeping pattern of their arms, often outlined by dark, dusty lanes. These dust lanes are not simply decorative. They mark regions where gas and dust are being compressed, triggering new waves of star formation as the galaxy slowly rotates. Within our own galaxy, this effect shapes exactly what we can and cannot see from Earth. Looking toward the crowded center of the Milky Way, we cannot see the galactic core directly. A thick band of dust, spread across thousands of light years, blocks the view almost entirely. For centuries, astronomers had no way of knowing what lay hidden at our galaxy's heart. It was only with infrared and radio astronomy, wavelengths capable of passing through dust more easily, that scientists finally peered through the haze, confirming an enormous black hole sitting quietly at the very center of the galaxy, hidden the entire time behind an ordinary, unremarkable cloud of dust. This same dust also plays a subtler role throughout the galaxy, gently scattering and reddening the light of countless faraway stars. An effect astronomers call interstellar extinction. Light traveling toward Earth must often pass through varying amounts of dust along the way. Astronomers must carefully account for this in nearly every measurement they make. A quiet, persistent reminder that even starlight reaching your eyes tonight has likely traveled through ancient clouds of dust. This same scattering effect extends far beyond our own galaxy, shaping how we perceive countless distant galaxies as well. Some galaxies, viewed nearly edge-on from our vantage point on Earth, display a strikingly thin, dark band running directly through their bright, glowing disk. The combined shadow of countless dust clouds, all aligned roughly along the same flat plane, where the galaxy's stars and gas are concentrated. Other galaxies, richer in gas and dust, and actively forming stars at a rapid pace, can appear dramatically dimmer and noticeably redder, invisible light than their true underlying brightness would suggest, simply because so much of their light is being absorbed and scattered by dust before it ever has the chance to reach our telescopes. Astronomers studying the most distant, earliest galaxies in the universe must account for this effect with particular care, since even modest amounts of intervening dust, scattered across billions of light years of intergalactic distance, can meaningfully distort our understanding of how bright, and how large, and how old these ancient, faraway galaxies truly are. Some of the most distant galaxies ever observed appear far dimmer than their true brightness would suggest, simply because their light passed through countless clouds of dust along its billions of years-long journey toward Earth. Correcting for this effect requires careful, patient calculation, comparing observations across many different wavelengths of light. It is a quiet reminder that even our understanding of the most distant galaxies depends on properly accounting for the humble, patient dust drifting between here and there. Some galaxies appear to contain so much dust that entire regions of active star formation remain almost completely hidden from ordinary telescopes, only visible through infrared light, capable of passing through the thick, obscuring haze. These hidden regions are sometimes called dust-enshrouded galaxies, quietly forming enormous numbers of new stars, invisible to anyone relying only on ordinary visible light to observe them. Astronomers sometimes describe these galaxies as cosmic furnaces, working quietly behind a thick, opaque veil, producing far more stars than their calm outward appearance would ever suggest. It is only by switching to infrared telescopes that this hidden, active interior finally becomes visible, revealing an entirely different, far busier picture than what ordinary starlight alone could ever show us. There is a simple, often repeated phrase in popular science: that we are made of stardust. It can sound almost like poetry, rather than literal fact, but it happens to be entirely true, in the most direct sense possible. Every carbon atom in your body, every oxygen atom you breathe, every atom of iron in your blood, was forged inside the core of an ancient star, released into space as dust. when that star reached the end of its life. That dust drifted for millions, sometimes billions of years, through the quiet emptiness between stars, before eventually becoming part of the cloud that collapsed to form our own solar system. Some of it became part of the sun. Some became part of Earth. A very small portion eventually became part of you. Rearranged countless times along the way, first into rock, then soil, then into the food that slowly built your own body. This is not simply a poetic idea. It is a direct, traceable, physical fact, confirmed repeatedly through decades of careful research in nuclear astrophysics. In a very real sense, every one of us carries material forged inside stars. Stars that lived and died long before the sun itself ever existed, scattered as dust across the galaxy, drifting patiently through darkness, until it eventually found its way here, into the particular, temporary arrangement of atoms that happens, for now, to be you. This idea was first articulated clearly, in scientific terms, by an astronomer in the 1970s, though the underlying nuclear physics behind it had been worked out gradually, over preceding decades, by researchers studying exactly how elements are forged inside stars. Different elements within your body have different stellar origins. The lighter elements, hydrogen in particular, trace their origin all the way back to the earliest moments of the universe itself, formed in the first few minutes after the Big Bang, long before any star had even begun to form. Carbon, oxygen, and nitrogen, by contrast, were built later, inside the cores of ordinary stars similar in size to our own sun, through the steady process of nuclear fusion occurring over billions of years. The heaviest elements, gold and platinum among them, required even more extreme conditions to form, likely forged during the catastrophic collisions of neutron stars, extraordinarily dense stellar remnants, in events so violent and so rare that scientists only confirmed this particular origin story within the past decade, through the direct detection of gravitational waves rippling outward from one such collision. It is worth pausing on how strange this makes your own body, in the best possible way. The calcium in your bones came from one kind of stellar death. The iron in your blood came from another. The gold in a ring, if you happen to wear one, came from something rarer still. A collision violent enough to briefly outshine an entire galaxy. You are, quite literally, a small museum of stellar history, walking around, mostly unaware of just how many different cosmic events contributed to your existence. This same fact applies equally to everyone you have ever known. Every person you love, every stranger you pass on the street, carries this exact same quiet history within them, built from the same scattered dust, forged by the same distant, long-dead stars. In that sense, every living thing shares a common origin, far older, and far more patient than most of us ever pause to consider. A quiet, shared ancestry, written not in family trees, but in the shared chemistry of stardust itself, connecting every living thing, quietly, across the entire span of time, from the first star to the last breath tonight. As we come gently toward the end of our time together tonight, let us sit with the strange, quiet patience of cosmic dust. A single grain, drifting through interstellar space, has no sense of urgency. It does not hurry toward a destination. It simply drifts, following the slow pull of gravity, for as long as it takes. Sometimes for millions of years, before finally becoming part of something larger. A star, a planet. Perhaps, eventually, a small part of a living thing, resting quietly at the end of a long day. There is a kind of lesson hidden in that patience, if you are willing to sit with it for a moment. So much of what feels urgent during an ordinary day would not register at all on the timescale cosmic dust operates within. Not because those things do not matter. They matter very much, within the small, precious span of a single human life. But there is something quietly comforting in remembering that the universe itself is in no hurry. You are allowed to borrow a little of that patience tonight. You do not need to rush toward sleep. You do not need to force your mind to quiet down all at once. You can simply let your thoughts settle, slowly, the way dust settles gently through still air, drifting downward, without effort, without hurry, until it finally comes to rest. Consider for a moment how much has already happened, quietly and patiently, simply to allow this exact moment to exist. Stars had to live, and burn, and eventually die, scattering their contents into space. That scattered material had to drift, slowly, for millions of years, before gathering once more into a new cloud. That cloud had to collapse, gradually, into a new star, surrounded by a spinning disk of leftover dust. That dust had to gather itself, patiently, grain by grain, into a small, rocky planet, orbiting at just the right distance from its star. And on that small planet, across billions of years, simple chemistry had to slowly become something more complex, eventually becoming the particular arrangement of atoms currently resting here, reading these words, breathing slowly, preparing for sleep. None of this needed to happen quickly. None of it needed to be rushed. Every single step took exactly as long as it needed to take, and not a moment less. You, too, are allowed that same unhurried timeline tonight. There is no need to complete anything else before you rest. No thought that must be finished. No worry that must be resolved. Just like the dust that took millions of years to become a star, your own tired mind is allowed to take exactly as long as it needs, tonight, to finally settle into sleep. There is no prize for falling asleep quickly. No penalty for taking your time. The universe itself, after all, rarely rushes anything. Stars take billions of years to live out their lives. Dust takes millions of years to become something new. Your own rest tonight can move at exactly that same unhurried pace, without needing to hurry toward anything at all. Let your breathing continue at its own natural rhythm. Let your body remain exactly as heavy and still as it wants to be. There is no schedule to follow tonight, no timer counting down, only the same patient, open-ended timeline that dust itself has always followed, quietly, without complaint, for billions of years. As we slowly drift back now, from the vast, quiet clouds of interstellar dust, from grains older than the sun, from the faint, silvery glow rising softly above the horizon, let everything we explored tonight settle gently into your mind. We began with dust that seemed too small to matter, and found that it built stars, planets, and every atom within our own bodies. We followed dust from the death of ancient stars, through the slow collapse of dark clouds, into the birth of new worlds. We considered the faint glow of dust drifting through our own solar system, and the extraordinary journey of a spacecraft that reached out to gently gather some of it home. We met grains older than the sun itself, preserved quietly inside meteorites. And we thought about the dust that drifts down through Earth's atmosphere, settling silently around us, nearly every day. Through all of it, one idea remained close. Nothing here is wasted. The dust of a star that died billions of years ago becomes the raw material for something new. Endings, in the universe, are rarely truly endings. They are simply quiet transformations, patient and unhurried, taking exactly as long as they need. There is nothing more you need to hold on to tonight. Let that dust continue its slow, patient drift, somewhere far above you, in the quiet dark. Let whatever thoughts remain from today drift away too, just as gently. And let yourself sink deeper, into a slow, unhurried rest of your own. Somewhere, right now, in some distant corner of the galaxy, a new molecular cloud is beginning its own slow collapse, following the exact same patient process we followed together tonight. That will not finish for hundreds of thousands of years yet. And somewhere else, an old star is quietly shedding its outer layers, releasing fresh dust into the darkness, adding, slowly, to the very same reservoir of material that eventually became the ground beneath you, the air around you, and the body currently sinking, heavier and heavier, into the comfort of your bed. This has been happening for billions of years, and it will keep happening for billions more, long after tonight, long after this particular night's rest has ended and given way to tomorrow, and the day after that. None of that needs your attention right now. It will happen exactly as it needs to happen, whether you are awake to think about it or not. Somewhere, right now, a grain of dust that has drifted for 1 billion years is finally settling onto the surface of a quiet, distant world. And somewhere else, a new grain is just beginning its own long journey, freshly released from a star that has just reached the end of its life. This slow exchange never stops. It continues, patiently, regardless of what happens here on Earth, regardless of whether anyone below happens to be watching. There is a quiet comfort in that continuity. Whatever happened today, whatever tomorrow eventually brings, this same slow, patient exchange of dust and starlight continues, entirely unaffected. It has been happening since long before you were born, and it will continue long after, steady and unhurried, exactly as it always has. Whatever you carry with you tonight, whatever thoughts or worries followed you into this quiet room, they are allowed to rest now too, gently, alongside everything else settling into stillness around you. If you are still here with us, another quiet journey is waiting for you soon. And if tonight's journey helped carry you a little closer to sleep, a like, a subscribe, or a gentle comment helps other tired minds find their way here too. There is nothing left to think about tonight. Nothing left to plan, or solve, or worry over. Just this quiet room, this soft darkness, and the slow, steady rhythm of your own breathing. Somewhere above you, invisible in the darkness, ancient dust continues its slow drift through the space between the stars. Patient, unhurried, taking exactly as long as it needs. You are allowed that same patience tonight. You do not need to hurry toward sleep. You only need to let go, gently, the way a grain of dust settles slowly downward through still, quiet air, drifting, without effort, until it finally comes to rest. Let your body remain heavy, and warm, and still. Let your thoughts continue to soften, and fade, and drift apart, like distant starlight scattered gently through a thin, quiet haze. Whatever tomorrow holds, it can wait. For now, there is only this room, this breath, and the slow, patient dark, settling gently around you. The same dark that has cradled dust and stars and quiet worlds for billions of years. And that now, for tonight, simply holds you too, from the sleep journal, and from one tired mind to another, across the soft, patient dark of tonight. Sleep well, rest gently, and good night. Think back, for just a moment, to where we began this evening, with a single grain of dust, smaller than anything your eye could ever hope to see, drifting quietly through the space between the stars. That grain did not know it would one day become part of a planet. It did not know it would one day become part of a person, resting in a warm bed, listening to a quiet voice describe its long, unhurried journey. It simply drifted, patiently, for as long as it needed to. You are allowed to rest in that same unhurried way tonight, not forcing sleep to arrive, not measuring how long it is taking, simply drifting, the way that dust drifts, patient and unbothered, letting the night do its own slow, quiet work, however long that happens to take. Somewhere far above you tonight, that same slow, patient drift continues, exactly as it always has. It does not need your attention to keep going. It does not need your understanding to remain real. You are free, completely, to close your eyes now, and let it drift on without you, exactly as it always does. Every single night, whether anyone is watching or not, there is nothing left for you to check on tonight. Nothing left to make sure of, before you finally let go. The dust will keep drifting. The stars will keep burning slowly, and you are allowed, completely, to stop paying attention to any of it, for now, and simply rest. Let this be enough for tonight. No more facts to remember, no more journeys to follow. Only quiet, patient stillness, exactly like the dust drifting somewhere far above you, content simply to exist, undisturbed, until morning finally arrives. Sleep well. Rest gently. And good night, from all of us here at the Sleep Journal.